In this lesson, we're looking at the difference between refraction and diffraction. Refraction is where we find the bending of light as it goes from one medium to another, whereas diffraction is the separation of the wave lengths as it goes through slits in a grating. So when we look at refraction, if you have a very long wavelength such as red, then you're not going to bend as much as when you're going from one medium to another, like if you're going from prism into air. Whereas violet, which has a very short wavelength, will bend substantially more as it goes from one medium to another. In diffraction, what we find is that we see the reverse here. We see the reverse because it's not the bending of it. We're not going from one medium to another. We're staying in the same medium. But what we're seeing is instead of having here in refraction where we have so here we see in a rainbow, such as this will be our violet, and this will be our red. And in between, we'll see green. Okay? So we have the short wavelengths bending more. Violet has a greater bend to it than red does. But in diffraction, we see the opposite happening. Short, long wavelengths, we'll keep them the same. Long wavelengths will diffract more. And short wavelengths will diffract less. So if we were to look here, we would see that this line versus that line versus this line, in comparison to the zero order or the central line, this is going to be red. It diffracts more, green in the middle, and violet will diffract the least in relation to the central line. That's really important. And then the other quick lesson that I wanted to talk to you about was polarization. Polarization is a theory that helps support the concept that EMR is a transverse wave. And by transverse wave, we mean that the wave propagation or the movement of the wave is perpendicular to the wave oscillation, so the motion that the wave is going through. So if your wave is traveling in this direction, if this is the direction of your motion, your wave is going to go up and down like this. Okay, that's what we're talking about, a transverse wave. And a polarized wave will only vibrate in one plane. So when we look at this diagram here, we can see that waves travel in this direction, they travel in this direction, they travel in this direction, and we just keep going around. We only ever look at something in one direction, but it's always traveling in multiple directions. So let's look at this wave that's moving here. This one we know is absolutely perpendicular. And so we're going like this, and it's here, and down in here. the slits are going in this direction, so the wave that's traveling in this motion is going to make it through these slits and go through. But when we rotate the polarized filter 90 degrees, when we rotate the second filter 90 degrees, the waves that are traveling in this direction can't fit through the slits that are going this way. It blocks it out. So that's the concept that's behind polarized lenses, transitional lenses for people who wear glasses, that when they walk outside and the sunlight hits their glasses, they turn a very dark tint. And when they come inside and they're away from the natural lighting, that they return back to clear glasses. Now the lights that we have in schools and offices, they're designed to mimic natural light because we spend so much time indoors. And so that's why some people's glasses never go quite 100% back to clear tint, because these lights are designed to mimic the sunlight that we have outside. Okay, so the fact that we can polarize EMR shows that EMR is a transverse wave and that it's perpendicular. And then there's 9 questions and the practice problem. I'll go through the practice problem with you here. It says, describe 2 methods to separate or disperse white light into all of its wavelengths. Compare the spectra, so the Roy G. Biv, that are produced from each method. So one method is to shine a light through a prism, right? So if we shine a white light into here, as it travels through the prism and then comes out, it's going to come out at red, orange, yellow, green, blue. Okay, so we can disperse it through a prism, and this is when we're looking at refraction, we're considering Snell's law. Okay, so wavelength 1 over wavelength 2 is equal to the index of 2 over the index of 1. It's also looking at the angle, it's looking at a number of different components. Okay? The second method would be to shine this light through a diffraction grating. So a diffraction grating is something that's got a number of slits inside of it. And the thing that we want to remember is that the closer those slits are to the size of the wavelength, the more diffraction that we're going to see. So when you shine a light into here, actually I'll turn this so it makes more sense. Okay, so this is the card turned this way so that we can see those slits, and then the light goes through here. Keep everything the same. So the white light comes into here. And we see that as it comes in through here and comes in through here, we have this happening. Where this is dead in the middle will be our central line. And we'll have different orders of brightness. Okay, and this will be red will diffract more, and violet will diffract the least. Okay, so you notice it still goes in the same color order, R, O, Y, G, B, V, but what we have on the top is we have red bending the least here for refraction, and for diffraction we have red bending most. And so when we're looking at diffraction, we are looking at Young's double slit experiment. And the formula that we're looking here is lambda equals d sine theta over n. So when we look at this relationship, lambda is proportional to sine theta. Okay, so your wavelength is proportional to the angle that we see. So as your wavelength increases, your angle of theta increases. So longer wavelengths get diffracted more.